Good afternoon. Welcome at the plenary session of the EAS annual meeting on Wednesday. I think we have a very exciting program today, and it will be 3 lectures that will be given by Professor Amina Helmi, by Dr. Agnes Kospal, and by Professor Günther Hasinger, and is followed later then by the General Assembly of our European Astronomical Society. But let me first introduce myself. I'm Lex Kaper. I'm one of the vice presidents of the European Astronomical Society, and it is a big honor to be here to introduce you to our speakers of today. We start today, and we have a tight schedule, so I try to keep it short, but we start today with the Woltjer Prize Lecture winner, Professor Amina Helmi. She works at Kaptein Institute of the University of Groningen, and her field of expertise is galaxy evolution and dynamics, and specifically the galactic archaeology, and her work recently on Gaia, which has of course gotten a lot of attention. She obtained her PhD in Leiden, and then with several grants did her work at the University of Groningen, now at Kaptein Institute, and she got many prestigious awards like ERC grants, Fichte grants from the National Science Foundation. She's a member of the Royal Academy of the Netherlands, and I think a very remarkable event was this year when she received from the King the knighthood in the Order of the Dutch Lion, which is a very prestigious award. As I said, I want to keep it short. Amina has done a lot of interesting things. She is nowadays also responsible in Dutch astronomy for the scientific directorship of our Dutch research school. But that is, of course, part of her work. She will now concentrate on the reason why she is here, is the receiver of the Woltjer Prize Lecture, which will be entitled New Views of the Galaxies. But before we start, I think we should demonstrate that this is really a prestigious award from our society. And Mark, I don't know whether you can show the diploma that has been prepared, but of course will be given to her as soon as we can. And so Amina, I want to give you the floor. I will give a warning at some point, and I'm very much looking forward to your talk on the new views of the galaxy.
Thank you very much for your kind words. I will start sharing my screen. I have to say I'm truly honored to deliver the Woltjer lecture today. As I told Roger when he informed me over Zoom, I didn't, and I still don't have enough words to describe how heartwarming this award feels to me. So thank you very, very much. So this is also why I would like to right away delve into my lecture on new views on the galaxy. And of course, these days, if you talk about the galaxy, you have to talk about the amazing results from the Gaia mission. But before I do that, I want to pay a small tribute to Woltjer, because I think it is fair to say that we as a community are really standing on the shoulders of a giant. Not only because of his scientific contributions, but I think in the words of Tim Deseu last year at the EAS, we do owe him as a community very much. He was a founding president of the EAS. He played a key role in the strategy to get the VLT as in the form of 4 8-meter class telescopes with a great suite of instruments with a VLTI. And he also played a key role in ESA's Horizon 2000 Plus exercise, which actually identified Gaia as a possible cornerstone mission. So I am particularly grateful to him for that. But I'm also grateful to the collaborative spirit of the galactic community, because as Woltjer put it, cooperation is a very good thing with mutual benefits for everybody. And so I would like to thank all of the 500 and more astronomers and engineers that are scattered throughout Europe and that are part of the Data Processing and Analysis Consortium, and particularly also Anthony Brown as chair of DPAC for all of the work and the amazing in producing the amazing Gaia catalogs. And I would also like to thank all of the PhD students and postdocs, past and current, that have contributed to the work over the years in my group, and also to some of the work that I will be presenting today. So big thanks to all of them. Right, so the Gaia mission, as you know, was launched in 2013 and has produced already 3 public data releases, which are truly changing the field. And the reason for that is that for roughly 1.5 billion stars, we now know how these stars are distributed in space. We know their motions on the sky, their proper motions. We have magnitudes and colors for all of these objects. And for a small subset, we have the line of sight velocities. And with such a vast data set of incredible quality, there is a lot of science that one can do that goes from the scale of solar system objects to star formation, to the galaxy itself and its dynamics and formation, to the distribution of mass in our neighbors, and also in the most distant quasars, where we are actually beginning to resolve their host galaxies. But of course, in this lecture, I cannot discuss, I don't have the time to go into detail into all of this amazing science that's been produced. And so I wanted to focus on 2 topics where Gaia has really been truly revolutionary: on the assembly history of the galaxy and on the dynamical state of the galaxy today. So let me right away start with the assembly history of the galaxy. So if you want to figure out how the Milky Way was put together, in particular understand its merger history, then we really should be looking at the galactic halo. In the halo, we find the oldest stars, those that are most pristine. And so they actually tell us about how the galaxy was put together, because this is where we expect to find merger debris. We can use stars as fossils in the sense of that stars remember in the way they move, in their age distribution, and in the chemical composition, which reflects the medium in which they were formed, that traces their origins. And so substructures in these observables pinpoint to the different accretion events that a galaxy could have experienced. So if you take a cosmological simulation and ask yourself, how are galaxies built? The halos of these galaxies are built via mergers. And what you see here is that in particular, the outer regions of the halos show a lot of substructures, spatially coherent substructure. Here, the different colors correspond to stars formed in different objects. And so you can see that we could identify substructures in the outer halo that would immediately tell us about accretion. And this is indeed what observations have told us now for a while, particularly observations from wide field surveys, where by looking at distant halo stars, we find a lot of substructures in the outer regions of the galaxy. Now, the issue becomes, if you want to go further back in time, and if galaxies form inside out, as we believe, then what you really care about is what happened in the inner regions of the galaxy. And what you see here in these simulations is that the material is very mixed spatially. So what you need is kinematics. So if you take, for example, a simulation of a small galaxy disrupting in the around the Milky Way, what you see is that even though the stars are distributed everywhere, if you look in a small volume around the sun, for example, you might expect stream of stars crossing that volume, telling you that these stars formed elsewhere. And so the prediction has been for a while that it should be several hundreds of spatially mixed streams. But of course, the problem has been we didn't have the velocity information needed to be able to test these hypotheses and test and recover the merger history of the galaxy. So this is, of course, where Gaia comes in. So what I'm going to focus now is on a small region around the sun of roughly 1 kiloparsecs to study the halo near the sun, to look for substructures associated to these merger events. And really what we have learned over the past years is that this is a story with two main characters. So if you plot all of the stars in this volume around the sun, of course, most of the stars are in the disk of our galaxy and are moving like the sun, are 220 kilometers a second. So what I'm plotting here is rotational motions and random motions. So most of the stars are in the disk, rotationally supported, and then you move into the realms of the thick disk, which have slower, are rotating more slowly, and have more random motions. Now, beyond this red semicircle would be the region that we dominated by the halo. And what you then see is that the halo near the sun is dominated by two components. Basically, one component that moves in the tail of what would be the thick disk, so a hot thick disk, and a second component, a blob or a sausage, that has slightly average retrograde motion, as well as some other substructures like this arc. Now, it's rather peculiar that this component that is, say, not thick disk has motions that are in the opposite direction as the vast majority of the stars in the galaxy. Now, Gaia has also allowed us to look at the stellar populations of these halo stars. And what this has revealed is the presence indeed of two stellar populations, again, two components, where the stars in this blue sequence correspond to stars in the blob, and the stars in the red sequence correspond to the stars in the hot thick disk. What's interesting is if you then now zoom further or study further the stars in this particular structure, it turns out that in chemical space, they define a separate sequence, a distinct sequence, separate from that of the thick disk or the thin disk, which are formed by stars born in our galaxy. The fact that they follow a separate sequence tells you that these stars were born in a different object. And the fact that most of the stars formed in this object, most of the stars near the halo that are not in the thick disk formed in this object, actually tells you that most of the stars near the sun in the halo formed in an accreted object. From the properties of this sequence, we can tell that its stellar mass was of the order of 6 × 10⁸ solar masses, so a relatively large system. And we can also, so what we're saying is, so there was this big accretion taking place, but when did it take place? And how did the Milky Way look like at that time? It turns out that if you look at the stars that have the highest metallicity, so the ones that would have been the last to form in this object, that tells you when the object was basically probably fully disrupted. This event happened about 10 gigayears ago. It turns out that there are stars in the thick disk that are even older than that. So when this happened, this event happened, this accretion event happened, there was a disk in place. This was a high mass ratio of about a quarter. And so this event must have led to the formation of the thick disk at a redshift of around 1.8. So I'm going to show you so this was basically a milestone in galactic history. And this simulation depicts roughly how that probably happened. So you see the accretion of a dwarf galaxy by a Milky Way like this, and how this disk puffs up. So really it was a milestone because both the stellar halo and the thick disk were triggered through this event. And we know fairly well the configuration of the event. So this must have been a retrograde encounter with a rather heavy disky satellite on a roughly 30 degrees inclination orbit. And because it was such a massive object, we called it Gaia Enceladus. And you can see Enceladus was a giant, and you can see how here it's being engulfed by a galaxy like the Milky Way. Now we know much more about the sequence of events that took place at that time. And this is very nice work from Carme Galar and collaborators, where again, she looked at the distribution of stars in rotational motions, again, random motions. We see again the blue sequence or Gaia Enceladus, the red sequence or the hot disk. She also looked at the distribution of ages in the thick disk. And what she found, what these authors found, was that the red sequence and the blue sequence, so Gaia Enceladus and the thick disk, hot thick disk, have similar age distributions, but that the canonical thick disk actually basically peaks around the time between 10 and 8 gigayears ago. So what this actually means in terms of what happened at the time is that Gaia Enceladus fell in, there was a disk there, it got puffed up, it got dynamically heated, as you saw in the simulation, producing this hot thick disk. But because the Milky Way was gas-rich at the time, that event plausibly, very plausibly triggered the formation of the traditional or canonical thick disk. Now, this is not the only object that we know of in the solar vicinity. A clustering algorithm can allow you to identify other merger debris. And so now, instead of looking again into velocity space, I'm going to move on to the space defined by energy and angular momentum. And so the idea is that these quantities are integrals of motion or change little, such that if an object is accreted, it will define a clump in this space. And so if you run a clustering algorithm in this space, then you can identify a lot of substructure. And that is indeed what we have been finding, quite a few substructures on top of Gaia Enceladus and the hot thick disk. So what's interesting about these substructures is not so much finding them, as it is the fact that they allow us to build a bridge towards what happened in the early universe, because these are the relics of the galaxies that were accreted at very early times. And so they allow us to understand how galaxy formation and plausibly also star formation took place in the early universe. Another thing that's interesting about these objects is that they probably did not fall in isolation, but they may have come with their own globular clusters and perhaps even dwarf galaxies. So thin streams are particularly interesting. And this is a very nice work by Rodrigo Ibata and Kiati Malhan, who developed a stream finder algorithm to identify using Gaia data, the proper motion and the photometry, many streams. And you can see a plethora of streams having been identified with this algorithm. And what's interesting about these streams is that, again, if you look at energy versus angular momentum, is of course they define all of these tight clumps, but the distribution is not random. They're actually associated to the different building blocks that we have identified already on the basis of the stars. So these thin streams, some of them at least, are associated to these building blocks. They are not all independent, which is important for dynamical modeling, as I'll discuss at the end, but they also reflect a population of disrupted small galaxies and globular clusters. But what about the globular clusters that actually have survived until the present day? We can also look at, again, energy and angular momentum. And what you see is, as dotted points, is the distribution of stars near the sun, and the solid white points are the location of the globular clusters in this space, which has been determined, again, because we know the proper motions of these systems much better since Gaia DR2. And so what you see here is that there is indeed a large concentration of globular clusters around the region occupied by Gaia Enceladus. The same thing is true for the Sagittarius dwarf galaxy. It actually turns out that about 50% of the globular clusters of our galaxy have been accreted. So it is as if these galaxies brought their own system of globular clusters. And this is also confirmed if you look at age metallicity relations for, say, the globular clusters associated to the different systems. So for example, this is the case of Gaia Enceladus. You can see that they follow a very clear age metallicity relation, which is consistent with what you expect from the dynamical masses derived from these building blocks. So with all of this, we now have a sketch of what we think has been the merger tree of the Milky Way. And we have been able to go back as far as about, say, redshift 2. This is a fairly incomplete picture of the merger tree because we are not yet very sensitive to very small objects, but we're also not sensitive to what happened before, say, redshift 2 or so. So we expect to be able to go even further back in time in the future with more data. So let me now try to move onto the present day, not focus anymore on the past, but on what is happening with the galaxy today, and focus in particular on the dynamics of the disk of our galaxy. So again, if we look at the kinematics of stars in the vicinity of the sun, and we plot their velocities, so I'm plotting here rotational velocity against velocity in the galactic plane in the radial direction and vertical velocity above and below the plane. What you immediately see from these distributions is that they're very rich in substructures. They're very rich in features. You see arcs, you see shells, you see bimodalities. In particular, this structure here, Hercules, was known to be due to the galactic bar. But what about the rest of the features that we're seeing? So as soon as you see a shell, what you know actually is that this is you need to make a phase space diagram, so plotting the vertical velocity against the distance from the galactic plane. And what this revealed was the presence of a snail shell. So what is this? So how do you produce this? This is a textbook example of phase mixing. If you perturb the disk by something like 5 kilometers a second, and you let that evolve in time, that produces a snail shell, a phase space spiral. And from the separation between these two shells, one can actually tell when the perturbation took place. And it turns out that this perturbation took place around the time that the small dwarf galaxy, the Sagittarius dwarf galaxy, came closest to the Milky Way, something like 0.5 gigayears ago. This has also been demonstrated by much more sophisticated numerical simulations of the interaction of Sagittarius dwarf galaxy with the Milky Way, where we see that the Milky Way is oscillating and that is able to produce a phase space spiral, as we can see here. So what does this mean? This means that a galaxy like the Milky Way is not an island universe, that we need to take time dependence into account if we are going to model it dynamically. For example, to try to determine the dark matter distribution around our galaxy. In fact, there's some work, very recent work, showing that you can actually use this phase space spiral to try to constrain how much dark matter there is in the solar neighborhood. But the other thing is that not only Sagittarius is perturbing the disk of the Milky Way, there is also the LMC falling in. And the LMC is producing among the distant halo stars, it's actually perturbing the halo, sloshing it, as it were. And that produces a dipole in the distribution of halo stars, as well as leave an imprint in the motions of these halo stars. So what this tells us is that the Milky Way is a very dynamical system. And it's not only affecting the thin disk or the halo of our galaxy, it also is affecting thin streams. So for example, there's the orphan stream that you can see here. The stars in the orphan stream are not streaming along the stream as one would expect, but what you see is that their motions in some regions are actually away from that stream itself. And that can be explained due to the inflow of a massive large Magellanic Cloud. Now, the streams are extremely interesting, and it turns out that they're much more complex. We're learning they're much more complex than what we thought before. And so this is another stream, the GD1 stream, where you can actually see that it's not smooth by any means. What you see is the presence of caps and spur and a blob. So why is this interesting? Potentially these streams can reveal the presence of the myriads of cold dark matter subhalos that cold dark matter models predict should be orbiting the Milky Way. So let me just now summarize by saying, I think these are truly revolutionary times for galactic astronomy. We're learning a lot about the merger history of the Milky Way. And I think this is particularly exciting because the characterization of the different building blocks allow us to learn about star formation and galaxy formation at very early times. But to be able to do that, we need to combine kinematics, photometry, and chemical abundances. For this, very large samples are needed. And this is, in fact, the focus of some of the symposia and special sessions that are taking place this week. The other point that I hope you remember is that the Milky Way is not in equilibrium, but it's dynamic because of interactions with its neighbors. And this leads to time-dependent effects. So if we want to fully leverage on the cosmological potential of the Milky Way to constrain the nature of dark matter, we really need more sophisticated dynamical models that take into account all of these effects. And this is indeed the focus on one of the special sessions taking place on Friday. So with that, I would like to stop and thank you very much.
Thank you, Amina, for this amazing perspective on our galaxy. We miss now really the big applause that you would have heard from all those 596 people that have listened to your presentation. And so it's wonderful. It also demonstrates Günther must be proud that this has been done also, of course, with the help of the Gaia satellite. It's amazing work. So, Mark, I wonder whether there are any questions that people have asked.
So currently there are no questions, but people will slowly put them in. Feel free.
Well, what I could do is to give Amina perhaps a little opportunity to go a little bit further on the bridge to the early universe. So you mentioned also in your summary slide that you want to compare now to observations, of course, of the high redshift universe. And so perhaps you could allude a little bit on that.
Yeah, one of the things that's particularly interesting is if you look at the chemical abundances of these very meta-poor stars. These are presumably some of the first, second, third populations of stars that formed in the galaxy. And so there's evidence of different types of supernovae, hypernovae that have taken place at early times. There's different chemical enrichment. We see evidence of perhaps neutron star mergers helping enrich these systems. So there's a way of understanding, if the IMF was different in any of these small objects. These are difficult to access even with a telescope such as JWST. So I think there's lots of things that are potentially in those data sets that can allow us to really gain a complete picture of what happened in the, say, early years of the universe.
Thank you. So Mark, is there a question?
Yes, there are some questions. There is a small technical glitch which doesn't make me see them at the right spot, but one by Michal Bilek. Do the Gaia and Enceladus stars form distant tidal features? If so, would we be able to detect such features in external galaxies?
Yeah, so Gaia and Enceladus, the event took place a really long time ago. So most of the tidal features will have phase mixed away. In particular, that arc that I showed in the kinematics of the stars is probably related to an arm from this tidal tail. I think we should be able to, and there's lots of new results, for example, from Dragonfly detecting substructures. There's very nice work from David Martinez Delgado identifying tidal streams. So this is also opening up for external galaxies, and there's a lot to learn from those as well.
I think we have time for one more question. And of course, the advantage of using our Slack channels and so is that Amina will be able to also address any remaining questions at a later stage.
So the next question is from Rice Taylor. I hope I not pronounce the first name correctly. Thank you for an excellent talk. Does the merger history revealed by Gaia shed any light on the missing satellite program?
Yeah, that's a very interesting question. I think it's early days to say this. One of the things that we hope to constrain as we identify different small objects that have been disrupted is to find, determine what is the luminosity function of the objects that have been accreted, and in that way put constraints on this missing satellite problem.
Okay, thank you, Amina. So thanks again for your amazing talk, and congratulations, of course, again with this Woltjer lecture award.
Thank you.
Thanks for your time in preparing this and giving insight. It was really wonderful. So I would like now to introduce the next speaker of a plenary talk. It is Dr. Agnes Kospal from the Konkoly Observatory in Hungary. She is leading a research group on astrophysics supported by an ERC grant and by the Hungary Academy of Sciences, and her research field is on the formation of sun-like stars, and especially the young eruptive stars and episodic accretion. She is, of course, working on the field of low mass star formation, and she also got in 2017 a special recognition from the L'Oréal UNESCO for Women in Science International Rising Talents Prize. And so we, of course, are very honored that Agnes is able and willing to give a talk for all of us. And now we again are at the 600 participant level. So we have a very big audience, Agnes. I try to keep it short so that most of the time can be spent by you on your talk. So perhaps you could upload your presentation.
Thank you, Lex, for the nice introduction. And of course, the honor is mine. And so I would like to thank first the organizers for inviting me to give this talk. So today I put the study of star formation into the limelight. Star formation, of course, is a very broad topic, and I have a little time now. So I'm going to focus on a specific issue within star formation, the topic of young outbursting stars. These objects temporarily increase their brightness by several orders of magnitude. They illuminate their circumstellar environment, and as such, they put themselves into the limelight, so to speak. This allows us to study details of the star formation process that would otherwise remain inaccessible. I will talk mostly about projects I'm working on in collaboration with many excellent colleagues in my ERC group, and of course with other colleagues too numerous to list here, but of course I'm thankful to all of them. But before going into the details, let me advocate the research of star formation a bit. The study of star and planet formation is a fascinating field of astronomy that often motivates the construction of the largest telescopes and most sensitive instruments. Thanks to the significant development of observational and numerical techniques in recent years, we now have a good general idea of how sun-like stars and their planetary systems form, which is based on observational evidence, and the underlying physics is supported by theoretical work and numerical simulations. By studying currently forming stars and planets, we hope to eventually understand the past of our own solar system as well. While the image I'm showing here is an artist's depiction of a forming star, we now have real images of the most important stages of this process. According to the general paradigm, the formation of sun-like stars starts in giant molecular clouds, where the densest parts of long filaments collapse under their own gravity to form cloud cores. Stars form at the center of these cores, and at the beginning, these are still embedded in their natal cocoon. Due to the conservation of angular momentum, the material quickly forms an accretion disk that feeds material to the forming star, and that becomes the birthplace of planets as well. Eventually, in a few million years, most of the disk material is used up, the rest is dispersed into interstellar space, and what remains is a mature exoplanetary system. Of course, this is a complicated process with many details, where important things happen at vastly different spatial scales. If you want to form a star from the interstellar matter, you'll have to take some material from a several parsec long filament and compress it to within 1 solar radius. That's about 8 orders of magnitude difference to overcome. You have to increase the density from 1,000 atoms per cubic centimeter, typical for the ISM, to 10 to the 26 at the center of the sun, and increase the temperature from 10K to 10 million K. Even if you leave out the interior of stars and just look at the physical properties within the circumstellar disk, these properties vary by orders of magnitude, and things change with time too, as we will see. The most fundamental process during star formation is accretion, the transport of material within the disk and from the disk onto the protostar. I'm showing here an artist's view of the accretion process, a scientist's sketch highlighting the most important elements, and an actual hydrodynamical simulation of the inner part of the accretion disk. I really like that these 3 pictures are now somewhat similar. The accretion process, again, is very complicated, depends on many things like the density, temperature, ionization, or the magnetic field. And as such, it also varies with time and location in the disk. This sketch shows the time dependence of the accretion rate from the disk onto the star. You can see that protostellar accretion and disk evolution are not smooth processes that happen slowly over millions of years, but in reality is episodic. And the accretion rate shows sharp peaks when it increases by several orders of magnitude. There are indications both from numerical studies and from observations that it happens like that. In the following, I will mostly focus on the observational aspects. You can see that peaks in this sketch are called FUOR and XOR outbursts. FUORs and XORs are different classes of variable stars, collectively known as young eruptive stars. Young eruptive stars provide the observational evidence for episodic accretion. In these objects, the accretion rate suddenly increases by several orders of magnitude, reaching up to 10 to the minus 4 solar mass per year. As a consequence, their luminosity increases from a few solar luminosities to a few hundred solar luminosities. If we measure the light curve at optical or infrared wavelength of such an object, then what we will see is a brightening by 3 to 5 magnitudes. And that is a very, very significant increase because if you compare it to the change in total solar irradiance, that is less than 0.002 magnitude. And even regular T-Tauri stars only vary by 0.1 to 1 magnitude. Here you can see light curves of some famous young eruptive stars like FU Orionis and EX Lupi, the prototypes of the FUOR and XOR classes. And below I'm showing how such an outburst can also illuminate the reflection nebula surrounding the young star. These outbursts raise many interesting questions. In the following, I'll address some of the issues that I and my collaborators are studying now. You can imagine that such a significant change in the luminosity of a young stellar object will have a substantial effect on the circumstellar disk. But how exactly do outbursts affect disk properties? Can they affect the structure, mineralogy, or chemistry of the disk? Another interesting aspect is that if you take the peak accretion rate and the duration of the outburst, which can last for several years or even several decades, you'll find that a star may collect as much as 0.01 solar mass or 10 Jupiter masses in a single FUOR-type outburst. So these disks must be very large and very massive, and they probably have interesting substructures, right? But do observations support this? And why do young stars, or more precisely their disks, erupt at all? Do they become unstable in a viscous, thermal, gravitational, or magnetorotational way? Are they perturbed by a substellar or stellar companion? Do they capture a cloudlet or collide with a streamer? And how do they finish the outburst? And how are the disks replenished for a repeat performance? And the most important question, Do all young sun-like stars go through eruptive phases? To answer this question, we need to know whether the disks of young eruptive stars are similar to normal T-Tauri disks or not. Let's see what the expectations and the observational evidences are, starting from the effects of the outburst. What do we expect concerning structural changes? If we consider the smallest spatial scales, so the immediate vicinity of the star, we can expect dust evaporation, the increase of the dust sublimation radius during outburst, and probably pre-condensation afterwards. Considering the larger spatial scales and also longer time scales, the idea is that the increased mass outflow during outburst carves larger and larger cavities into the envelope. For a while, there may be some infalling material to replenish the disk and to start the cycle again. But eventually the envelope depletes and the disk-only protostar remains. According to this picture, repetitive outbursts basically make the protostars optically visible. But what do the observations say? Do they support these ideas? To trace the inner few AU spatial scales, we need to use, for example, infrared interferometry with instruments like the VLTI. During the outburst of V1647 Orionis, for instance, we indeed detect the changes in the inner radii of the disk and the envelope, which seem to be larger during the outburst than in quiescence, indicating the movement, the enlargement of the dust sublimation radius. To trace the envelopes and outflows, we can use molecular line studies at millimeter wavelengths with instruments like ALMA, the ALMA interferometer for high spatial resolution studies, and single-dish instruments like APEX for lower spatial resolution. ALMA studies show a wide variety of outflow morphologies, from large 10,000 AU scale outflows with very narrow opening angle to smaller few thousand AU scale outflows with very wide opening angle. And finally, we can find disk-only eruptive stars as well, where all we see is a 100 AU scale disk in Keplerian rotation. At low spatial resolution, we can survey large number of eruptive stars to search for outflows. What we found so far is that about half of them drive outflows, including some very massive and energetic cases. So far, so good. What about chemical changes? Outbursts may move the snow line or induce interesting chemical reactions that would not happen if there were no outbursts. Now, there are several time-dependent chemical model calculations that indeed suggest important changes in the molecular ice and gas phase abundances. In this example, I'm showing a model for a 50-year-long outburst, and this graph in the middle left shows the time evolution of the abundance of the formaldehyde molecule for different model parameters. The bottom panel shows one specific model, and it shows the abundances across the disk during the outburst in the gas phase and in the ice phase. You can see that during the outburst, almost all formaldehyde went into the gas phase. There's practically none in the ice phase. Such calculations can be done for other species as well, and this bar graph in the center shows abundances of different complex organic molecules before, during, and after the outburst in the gas phase at the top and in the ice phase at the bottom. Can we really observe this? Let's check with ALMA. Here I'm showing ALMA observations of the millimeter spectra of V883 Ori and Haro 5A IRS, two FUR-type young eruptive stars. You don't need to see the details. The point is that they're full of emission lines. The different colors indicate different species of complex organic molecules that I also listed here on the left. We know from astrochemical studies that these molecules form in the ice phase, typically on grain surfaces. They are observable in FURs, in young eruptive stars, in the gas phase, because they were heated and sublimated by the outburst. So FURs can essentially be used as astrochemical laboratories. We talked about ices and molecular gas, but what about the solid dust grains? What happens to them? This is a very interesting question because we know that the interstellar matter consists mostly of small amorphous dust grains. We can see this if we look towards the galactic center, where there is a lot of dust in our line of sight. On the other hand, solar system comets have dust that has a very high crystallinity fraction. How did it happen that the amorphous dust became crystalline? there's a process called thermal annealing that transforms silicate grains from amorphous to crystalline. This phenomenon happens at temperatures between 1000 and 1500 K. So you need to heat the dust up into this exact temperature range. This means that we can surely find lots of crystals, crystalline grains in outbursting stars, right? Well, we know of at least one example, EX Lupi. This star went into outburst in 2008, and using infrared spectra taken with the Spitzer Space Telescope, we found that during the outburst, the 10-micron silicate feature showed these peaks and shoulders that are characteristic of crystalline forestry. But before the outburst, the feature was completely amorphous. We interpreted the appearance of crystalline features as ongoing annealing, crystallization on the surface of the circumstellar disk of EX Lupi caused by the heat of the outburst. Follow-up spectroscopic monitoring revealed that the crystalline silicate grains later became more tenuous and colder, probably because they were being transported to colder, more faraway areas of the disk where comets may form. To confirm if crystals indeed reached the snow line beyond in the EX Lupi system, we need very, very sensitive observations to measure the weak signal from the crystals. This will now be possible thanks to the James Webb Space Telescope, where we managed to secure telescope time in the first cycle for this project. I mentioned earlier that we expect outbursting disks to be large and massive because a lot of material is needed to keep up the outbursts. What do the observations say? To trace disk mass, we need to observe them at millimeter wavelengths, where they're not so optically thick, and preferably model them using radiative transfer that properly takes into account optical depth effects with ray tracing. This is what we did for a survey of 10 FUR-type objects with ALMA, some of which I'm showing you here. These images display the disk continuum emission at 1.3 millimeter, and our radiative transfer modeling provided disk masses and characteristic radii. We also collected values obtained in the same way for other FURs to complement our survey, and also for normal class 2 objects, so theta-ray disks, and also for class 1 objects, so embedded young stellar objects, as comparison samples. You can clearly see that the FUR disks are typically more massive and more compact than the disks of regular non-eruptive young stars. This means that FUR disks are either different from the general population to begin with, or the outburst makes them somehow special. If we know the stellar mass and the disk mass, we can also check if the disks are gravitationally stable or not, which would inform us about why these disks produce outbursts. Gravitational instability is one of the possible trigger mechanisms of FUR outbursts I mentioned earlier. There are different criteria to check this, the simplest one being that the disk becomes gravitationally unstable if it is more massive than 10% of the stellar mass. Most of the studied FUR disks actually satisfy this criterion. It is still unclear whether we should see substructures like gravitational fragments in them. Some simulations suggest that they should be there, while some other recent numerical results indicate that given enough time, an ongoing eruption may actually dissolve these structures by heating and expanding the disk. Or maybe our observations just didn't have enough sensitivity and spatial resolution, because unfortunately, most of these objects are quite distant. Another interesting aspect of this study is that not all disks are massive. There are some that are quite low mass, among others the prototype FU Orionis. For some FURs, we measure disk masses comparable to the mass accreted in one single outburst. How do these disks erupt? Maybe we are just so lucky that we see the last eruption that these disks can produce, or maybe they will be replenished later. That's not something that can easily be proven. But there is one FUR where we could measure the replenishment, and that's V346 Normae. In this object, we detected a double-peaked line profile towards the center of the system in the 13CO and C18O lines with ALMA. This indicates rotation. By precisely measuring the velocity as a function of distance from the star, we found that the central part of the system is in Keplerian rotation, but outside of that, there's a pseudodisk whose velocity field is a combination of rotation and infall. From this, we could analytically calculate the infall rate. While V346 normally is in outbursts since the 1970s, in 2010, it had a brief quiescent period when we could estimate its quiescent accretion rate, which proved to be lower than the infall rate by more than an order of magnitude. This means that this object receives more material from the outside than what it can dump onto the star normally. This may cause a pileup of material in the inner disk, which may then become unstable and cause an accretion outburst. This is the first observational evidence for such a mismatch between the envelope to disk infall rate and the disk to star accretion rate in case of a young eruptive star. So this may not be a general answer, but it may explain why this specific disk is erupting. I already mentioned some of our ongoing projects, but what else is there to be done? I haven't emphasized this, but a class of young eruptive stars is rather small. Only 24 or so such objects are known, which severely limits statistical studies. However, this may change in the near future because currently ongoing large time domain surveys are helping us to discover new eruptions. I'd like to highlight one of them. Amina already mentioned Gaia in the previous talk. So the Gaia astrometric mission scans the whole sky regularly, and what is important for our purposes is that it publishes scientific alerts for objects with sudden large brightness changes. With follow-up studies, we can discover new outbursting young stars among them, as these examples demonstrate. You can see the optical and infrared light curves of one of them, Gaia 18 DVY here. We are collaborating with colleagues from Italy, Poland, and the US on spectroscopic follow-ups and have several papers in the pipeline, so watch out for those. Light curves from these surveys are also helping us revisit some classical objects such as V1057 Cygni and the V1515 Cygni, the second and third Fjord type objects discovered after FU Orionis itself. The latter one, for instance, seemed to be close to finishing its outburst according to our latest measurements, which is very rare among fjords because their outbursts tend to be rather long, especially on a postdoctoral timescale. Another interesting prospect, I think, is image reconstruction of infrared interferometric data. This is now possible thanks to MATIS on the VLTI, which will provide a great opportunity to study the inner disk structure in a model-independent way. We have several projects with snapshot observations, but hopefully we will find a good target for image reconstruction in the future. This has been a summary of the most interesting aspects in the field of young eruptive stars from my personal perspective. If you are interested in this topic or star and planet formation in general, I recommend signing up for the Protostars and Planet 7 conference, which will be held next year. For this, we are preparing a chapter on accretion variability as a guide to stellar mass assembly, where we will address the topic of young eruptive stars as well, from a somewhat different perspective from what I presented here. So I would like to finish with summarizing the main points I want you to remember as takeaway messages. I was talking about young eruptive stars, which are young star objects exhibiting powerful accretion-related outbursts. These eruptions may constitute a so far largely overlooked but potentially fundamental phase of the formation of sun-like stars. It is very important to know that the phase when eruptions happen overlaps with the time of planet formation in the disk. So the outbursts may affect where and what kind of planets may form. I show results from our extensive research program characterizing young eruptive stars at different wavelengths and spatial scales. I can't emphasize enough the importance of multi-wavelength, multi-scale studies to get the full picture. Our latest results suggest that the disks of young eruptive stars may be special, and there may be no single theory that explains all outbursts. I think that confronting the results on young eruptive stars with solar system evidences of temporary flux rises of the early sun, for example from meteorites, may provide important constraints for the models. So the jury is still out on whether all young stars go through these eruptive phases. Therefore, of course, more observations and more modeling are needed for a conclusive result. So we'll keep working on this, but I will stop with my talk now and take questions. Thank you.
Thank you very much, Agnes. I hear an amazing applause after your great talk of all the people that attended. So it's very nice to see also your future perspective. There is also still lots of work to do with JWST and other facilities. You seem to use all of them. So it's really nice to listen to your results. So Mark, you have a question.
Yes, well, indeed, there is one question, but our chair agreed that I give one question to you. Thanks very much for your talk, and Agnes, a very interesting topic that I am interested in as well. And I was wondering, what's your take from your perspective on the difference between EXORs and FURIONIS? As you know, this is a difficult thing to try to unite these two characters.
Yeah, so yeah, I think these kind of categories were very useful about 30 years ago when the first outbursts were recognized as accretion events. And of course, phenomenologically, like if you look at the time scales of the light curves, or you look at the spectra of these objects, then you see very distinct differences between them. So it's nice to categorize them to these separate classes. But then since then, I think we have to move past these, because now especially with the discovery of new outbursting objects, we see many of them which do not really fall into these neat categories, and there are some which have certain properties that are more similar to FURs, other properties of them are more similar to XORs. So what I'm most interested in is what these observed properties tell us about the underlying physics. And I suppose some of these observed properties should constrain what kind of theories, what kind of theories can explain their outbursts, or the end of the outburst, how you can switch on and switch off the instability in the disk. And I think that is probably, or that might be different for XORs, which can go up and down in a few months or a few years. And it may be very well something completely different for FURs, which go up once and then stay in the high state for a century. So there must be something different in the underlying physics. And for that, I think these categories are useful, but we have to look at the underlying physics.
Okay, Mark, you mentioned another question.
Yes, there is one repeated also by Agata. So the first one is by Alexis Quintana Isasi. Excellent talk. How far do you think that future Gaia releases could improve the accuracy of the results, and notably how one could visualize these outbursts?
So the Gaia science alerts are excellent because they provide the light curves of these objects. So as you may know, the Gaia data, the normal Gaia data releases do not contain the epoch photometry yet. But for the alerts, for interesting phenomena with large flux changes, these light curves are public now. So you can go to the alerts webpage, you look at the light curves, and from our point of view, of course, I mean, all these objects, or most of these objects, just by looking at the light curve, they are candidates, FUR candidates or XOR candidates, because we have to do some spectroscopic follow-up to confirm. Typically, we have to confirm first that they are young stars, that they are associated with a star-forming region, that they have the spectral characteristics needed to be classified as a young star and as an eruptive young star, especially. So some of the light curve shapes can be confused with other phenomena. So we need to add more observations to confirm this. So for Gaia, I think the light curves are very important. That's one aspect. The other aspect is, of course, distance. Of course, from the parallax, the successive Gaia data releases provide better and better estimates for how far these objects are. And of course, structure, the distance and structure of star-forming regions based on the new Gaia data releases are also being updated. So it is very interesting to see, for example, what the new Gaia data release would say about the kinematic and spatial distribution of young stars in a star-forming region, and where a young eruptive star fits into that picture.
So Agnes, thanks very much again. I hope, of course, that people in the audience take the opportunity of the Slack channels and so to ask you further questions. So thanks again.
Thank you.
So then I think it's now time to introduce the last speaker of today, which is Professor Günther Hasinger, the Scientific Director of the European Space Agency. We are very pleased, Günther, to have you among us to give an update on the ESA scientific program.
And thank you very much for the nice introduction, for the invitation. And yes, I'm glad that I can continue the tradition to give you an update of the science program. Unfortunately, in the 10 minutes, which I roughly have, it's very hard to cover the whole breadth of the program. So I will concentrate mainly on the most recent developments. The science program, as you know, is consisting of solar system explorers that are in our own solar system, looking at the sun and the planets, and then the cosmic observers, which are looking outward. And in each of these charts, you see basically the legacy missions on bottom, the missions that we are currently having in orbit, and then on the top row, the ones that we are currently constructing. And it is really an amazing breadth with 14 missions in orbit, 16.
So Günther, I don't think, at least I don't see your screen.
Yeah, indeed.
Oh man, sorry for that. Let me try to share screen. I forgot that, being too nervous. Okay, let me come back to the talk. Do you now see the screen?
Yes, we see all your slides, so you only have to select.
Okay,
yes,
okay, good. So I talked about this slide, 14 missions in orbit, 16 in preparations, 22 in the archival phase. And now I will just give you a few recent highlights, starting from the solar system side. This is a very nice movie that has been taken recently from a coronal mass ejection that has been observed with Solar Orbiter. And it shows very nicely the synergy between the different instruments. So you have the full field ultraviolet imager in the center. You have the coronagraph surrounding it, and then we have a very wide field imaging instrument that can measure the plasma very far out into the solar system. And this is one of the coronal mass ejections. You know that the sun is getting more and more active, and Solar Orbiter is getting closer to the sun, so we are really expecting a lot of excitement. Actually, very soon, both in August, both Solar Orbiter and BepiColombo will fly by Venus, and so we will have a chance for them to measure simultaneously the plasma around Venus. And that brings me to already one of the exciting recent developments. As you may have seen, we have selected the M5 mission, and it is actually Envision, a very powerful Venus exploration mission, which is covering 6 instruments. One of them is a radar provided by NASA. And as you may know, NASA has also selected 2 smaller Venus missions. So the next decade will actually have a very strong focus on Venus, which so far has been a little bit left aside. Now, a very exciting result that just came out a few days ago. CHEOPS, our small mission that is done in collaboration with the member states, with Switzerland in particular, and 10 other member states, is really making very nice and beautiful observations. This is a surprise finding that is a star which is visible with the naked eye. It's only less than 50 light years away. It was known that it has at least 3 planets, but only 2 of them were known to transit. And then when CHEOPS observed it, there was the third one, outer planet, which was photobombing, so to speak, the observation. And this is at a 100-day orbit, and it's one of the furthest transits of such a bright star, which we know. And so this object will now become a golden exoplanet for future studies with Hubble and with James Webb Telescope, and maybe also with Ariel in the future. And this is a comparison. So with the data, both from radial velocities and the transit, we can measure the density and the likely structure. And so planet D is actually something like a sub-Neptune super-Earth object, very likely dominated by water, ice, and gas. So it's not habitable, but it is actually close to where Venus would be in our own solar system. So it is a temperate exoplanet, very rare in our current samples. Then Amina, actually both speakers before have already talked about Gaia results, so I can be short here. This has already been shown by Amina, but Gaia is really a wonderful workhorse for us. It is mind-boggling how many scientific results are coming out. And Amina has already mentioned this result, basically showing the wake of the dark matter of the LMC coming into the galaxy and showing that the LMC is very likely on its first path to the Milky Way. Now, dark matter is clearly very close to our heart, and there are more exciting results about dark matter. This is a nice discovery, both from the Subaru telescope in Hawaii, and XMM Newton. Another one of these cluster mergers where you see that the hot gas, which is shown here in green by XMM Newton, and then the hot thin gas, which is shown through the radio observations with Green Bank, which is Sunyaev-Slodovich effect, are actually separated out into different regions. And this is another one of these puzzles, how you can separate out dark matter versus the normal matter. And there are two more exciting results from XMM Newton. This is actually a combination of eROSITA, which had its data release yesterday. And eROSITA has a very large field, and this is a cluster, and they have discovered an infalling clump along a filament into this cluster. And then XMM Newton and ASCAP and DECAM have done a more detailed observation, and you can see that there's a black hole with radio tails kind of flying behind the galaxy. And another very recent result from XMM Newton is a discovery of an orphan gas cloud, which is very likely a remnant of a falling in galaxy into a cluster. So this whole substructure studies of clusters is really fascinating. Now, the overall output of the ESA science program is still fantastic, and but you also see that in the last few years it is completely picked up by Gaia, which is now doing almost half of the all the papers that are coming out of the ESA science program, about 5 papers per day for Gaia. And when you compare that with the Hubble Space Telescope, which is a partner-led mission, Gaia is now since 2 years superseding the Hubble observations. But when you integrate over the whole Hubble legacy, then it's still dominating the whole field of astronomy. But let's wait for a few more years of Gaia, and I think we could also beat the integral of Hubble. Now let's come to the future. We have already heard about the James Webb Space Telescope. We are really very, very close to launching it. Yesterday was one of the final reviews, flight readiness reviews, and so it will be packed up and shipped to be launched towards the end of the year. And I'm very happy to say that the announcement of opportunity and the observing time distribution of the first year was very successful for Europe. Europe is actually receiving about 30% of the first AO on time. And so congratulations to all of you getting James Webb time. I'm actually also on a proposal that is getting time, so I'm looking forward myself to analyze Webb data. And the same excitement is still there with Euclid. Euclid is now fully integrated. It is being tested in Liège. We have still some problems with the detectors, but we are about to solve them. We are quite optimistic that we might actually solve them and launch Euclid also in time. And that brings me now to the last set, this last slide, because I'm very happy. And I would also like to thank the senior committee, and Amina Helmi is one of the members of the senior committee, for advising us on the priorities of science for the next piece of strategic planning. We have just had the Woltjer lecture, and we heard that he had a major impact on the Horizon 2000 Plus program that selected Gaia. We are currently in the Cosmic Vision program, And the next big missions, as you know, are JUICE being launched next year, and then Athena and LISA. And so this is now defining the future after LISA is flown. And it's very exciting. We have one priority, which is very likely the first large mission in the next phase, which is going back to the icy moon of the giant planets, maybe even trying to understand the geysers, the water coming out of the icy moons, and maybe even having a look for life in this water. The other one is a theme around exoplanets and the Milky Way. One of the possible solutions there is to build another Gaia in the near infrared, so where we could actually resolve all the star forming regions and get a very detailed look into the galactic center. And then finally, something very close to my heart, a probe of the early universe, either with a very high precision cosmic microwave study or with a next generation gravitational wave study. And for this purpose, we also have to develop new technologies, and there are a few critical technologies that we would like to embark on relatively soon. Cold atom interferometry, quantum sensors that allow very, very accurate measurements, X-ray interferometry, where we could get a picture of a black hole similar to the Event Horizon Telescope, and then new power and heat sources to go out into the solar system. And then ideally a cryogenic sample return where we could bring some of this icy material back from outside, from beyond the snow line, plus solar sails. So with this, I would like to thank you very much. I'm unfortunately very short in time, but I'm very happy to answer questions, and then also in the Slack channel if you would like to pose them. Thank you very much.
Thank you very much, Günther. It is impressive how you managed in only so few minutes to compress all these important things that have been achieved with ESA's missions, also some, of course, in combination with our Atlantic partners. But so please, Mark, if there are any questions through the Q&A.
There's one question by Agnes Kospal. Hello, Günther. Thank you for the great overview about the possible L-class exoplanet mission in the Voyage 2050 program. Do I understand correctly that the senior committee already has chosen the type of mission, mid-infrared spectroscopy, instead of the science theme, in parentheses, as was their remit? Does this mean that a reflected light, high contrast imaging mission will not be studied?
Actually, the whole remit of the senior committee was not to select missions or to recommend missions, but to recommend science themes indeed. And so the science theme is actually a temperate planet and the planets and the Milky Way. In this particular theme, we are actually focusing on temperate planets first, but we would like to start studies about the possible implementations. However, we realize that the temperate planet scheme could be extremely challenging. And so as a backup solution, we also want to study a near-infrared Gaia mission, which, however, both of them could in principle be implemented if the parameters are kind of right.
Okay, so Mark, was there another question?
There's one more from Alejandro Borlaf. Dear Günther, thank you for your talk. Is there any prospects for ESA to participate in lunar-based observatories similar to NASA's FarSide?
Yes, so indeed, the Human and Robotic Exploration Program is focusing on all the destinations where also human exploration can happen. And so the moon is part of their remit. And they are actually, they have one possibility of studying a radio telescope on the far side of the moon. This is in principle it's not excluded that the science program can also participate in this, but this is more a top-down infrastructure question, and therefore it is done by the Human and Robotics Directorate.
Thank you. So I don't know, Mark, whether the Slack channels and so have provided more questions that need to be addressed now or could be addressed, of course, later by Günther, as he already mentioned.
There are several more questions, at least on the Q&A facility.
There is time for one of them at least.
Okay, so I'll provide the one from Keith Smith. What's the status of the possible ice giant mission? Are we just waiting for the US decadal survey, or are there studies going on at ESA?
Yes, so we have actually studied possible implementations of ice giant missions already in preparation of the last ministerial meeting. And the option to join NASA in one of these ice giant studies was discussed. Actually, there's a very strong recommendation from the senior committee that we should also take into account partnering with another strategic mission. So both in the astronomy sector but also in the planetary sector. So a collaboration on an ice giant mission on an M-class level, as we have always discussed, is still on the table.
So Günther, thank you very much for this amazing talk. I also would like to thank the speakers again for their brilliant contribution to this plenary session. I all invite you to attend now the General Assembly, for which you all have received a separate link. And with this, I would like to close. And please, if you have any questions left for the speakers of this afternoon, do so via our Slack channels, and then they will be addressed. So thanks again, and I'm looking forward to see you again.